In this video, I'm going to prove the absent bit string rule. Now you can think of the absent bit string rule as an algorithm. It's an algorithm that, given any infinite list of infinite bit strings, it produces an infinite bit string that's not in the list. And so the natural way to prove this, and this is a natural way to prove lots of algorithms are correct, is using contradiction. The reason is because the absent bit string rule is constructive. It's a constructive thing. It says when you have an infinite list like this, this thing will not be in that infinite list. So it produces something. It always produces this thing. It always produces this thing that has this property that it is not in the list, that it's not in this original list. So the absent bit string rule always says that this thing can always be produced, and this thing is not in this list. All right, so the contradiction, using contradiction to prove this, what we're going to do is we're going to suppose that, hey, no, this thing B is in the list. So I don't know where it is, but let's say it's there. And then we're going to find a contradiction to that. The contradiction is going to be to this right here. All right, and so the idea is we don't really know where, we see, the thing is, we know that the absent bit string rule works. I'm sure that it works. We've seen examples of how it works. It's pretty clear that it works. So to prove that it works, we say, well, let's suppose that it doesn't work, and we find a contradiction. So supposing that it doesn't work, that means that the thing that it produces, this thing must be in the list somewhere. Now, where is it in the list? I'm not sure. Now remember, we know that it's not really in the list, but we're doing a proof by contradiction. So we're saying, well, suppose it is in the list. Okay, if it's in the list, well, where is it? Okay, I don't know where it is exactly, but the thing to notice is that each of these, the way that each of these work is you have, like say with this first one here, we have first row, first position, first row, second position, first row, third position, and so on. With this one, we have third one down, first position, third one down, second position, third one down, third position. Okay, so the way we're going to look at this is we're going to say, okay, suppose we're at position I. And so we're being completely general. So we're in row I. And so that's not, so it's being completely general. Row I is this thing right here. Row I looks like this, right? Remember row row 3 looked like this, right? 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and so on. Row I is going to be I1, I2, I1, I2, I3, I4, I5, and so on. Okay, and so that's how the proof goes. suppose that, so we know that this thing isn't in the list, but we're going to suppose for contradiction that this thing is in the list. Well, if he's in the list, then he's got to be equal to one of the rows. So here he's equal to one of the rows. He's equal to that. Now, what does it mean for two infinite bit strings to be equal? Right? We've talked about this. This means that each of the positions are equal. Okay, so this is going to if these are equal, then that means that those two things are equal. If these are equal, then that means that those two things are equal. If these are equal, then that means that those two things are equal. But remember, the key place that the place where we define these things to always be different is in the II place. And so most importantly, those two have to be equal. And that's exactly what we have right there. And this is where we'll find a contradiction. Right, by the very definition of this thing, they can't be equal. But supposing for contradiction that we did produce something in the list, well then what happens? These two things have to be equal. Well, if those two things are equal, then we have two possibilities. Either this thing is 0, that's case 1, or wherever they meet up is this thing is 0, or where they meet up it's 1, right? Because these are infinite bit strings, there's only zeros and ones. All right, so by our definition, let me clean this up. So we're in case 1 here. By our definition of capital B, capital BI, if little b, I is 0, then capital BI is equal to 1. And if they're equal, right, then by the definition, that says that 1 equals 0. That's a contradiction. 1 does not equal 0, right? And similarly in case 2, if these are equal, right, well then if this thing is, if little b, I is a 1, then capital BI is a 0. That's the definition. That's how we defined capital BI. So then again, we have that 0 equals 1, a contradiction. Right? So there's just no way for this thing to be in the list. So it's not in the list. And the absent bit string rule does what we say it does.